Welcome to iLecture Online, and today we're going to talk about magnetic fields and forces due to magnetic fields on moving charges. And yes, indeed, when a charge exists in a magnetic field and it's not moving, there's no force on the charge. And if a charge moves parallel to the magnetic field, the direction of the magnetic field, then there also will be no force on the charge. The only time that a charge object or a charge feels a force or experiences a force in a magnetic field is when the charge moves through the magnetic field perpendicular to the direction of the magnetic field. So I have a bunch of examples on the board here to try and figure out what the direction of the force will be on each of the charges as they're moving through the magnetic field. Remembering, of course, that the magnitude of the force can be found by taking the equation that the force on a moving charge is equal to the size of the charge Q times the cross product of the velocity of the charge times the magnitude of the magnetic field and the direction of the magnetic field. So force is Q V cross B, and of course when we want to find the magnitude of V cross B, this can be written as the magnitude of the force is equal to Q times V times B times the sine of the angle between them. Now, theta is the angle between the direction of the velocity of the charge and the direction of the B field, and you can see then if the angle between them is 90 degrees, which means if the direction of the velocity is perpendicular to the direction of the magnetic field, the sine of 90 degrees is 1, and the magnitude of the force simply will be QVB. If the angle between them is not 90 degrees, then of course the force will be less than QVB by this factor, and of course if the angle is 0 degrees between the direction of the velocity and the direction of the magnetic field, then the sine of 0 is 0 and the magnitude of force will be 0 accordingly. Alright, so what we're going to do now is we're going to try and find the direction of the force on each of these charges. You can see there's a charge here moving upward, charge here moving to the right, charge there moving to the right. Also notice that some charges are positive, some charges are negative, and that does make a difference. Now, the magnetic field is indicated by this B with an arrow on top of it, so we sometimes call it the B field or the magnetic field. And these arrows here are in the direction of the magnetic field. Here the field is to the right, here it's up. This means that the field is into the board. It's like looking at the back of an arrow where you see the hairs in the back there. So the B field is into the board. Here we're looking at the tip of the arrow, so the B field is out of the board towards you. Here again, the field is downward, the field is to the left. Here the field is out of the board, and there the B field is into the board. So based upon that, what will be the direction of the forces of each of those 8 charges in each of those 8 different magnetic fields? And I'll use a red pen to try and indicate it. The way that's done is that if it's a positive charge, you use your right hand for the right hand rule. If it's a negative charge, you use your left hand for negative charges to find the direction of the force. And so how do you do that? Well, you take your hand and you point your fingers in the direction of the velocity of the charge, and since it's a positive charge, I'm using my right hand, like so. Then you have to turn your hand whatever direction you need to, so you can curl your fingers in the direction of the B field. So I'm pointing upward, and then I point this way to show the direction of the B field. So up for the velocity, this way the B field, and then my thumb points inward into the board, so I can say then the force, and I'll indicate that with a little cross, the force then will be into the board. So velocity up, B field this way, force into the board. Looking at this example here, now of course I need to use my left hand because it's a negative charge. I point my fingers in the direction of the velocity of the charge. Then I have to curl my fingers in the direction of the B field. Of course I can't curl my fingers upwards, I have to turn my hand around. I can now curl my fingers upward and my thumb points into the board. So here also the force on this charge will be into the board. Okay, going to our next example. Here we have a B field that's into the board, but I need to use my right hand because it's a positive charge. Take my right hand, point my fingers in the direction of the velocity of the charge. Then I have to curl or turn my hand in such a way that I can curl my fingers towards the B field, which is into the board, and now my thumb points upward. So I can see now that the force on this charge will be upward. So it could go like this. Force is upward. All right, next example. Negative charge means I have to use my left hand. I point my hand in the direction of the velocity, which is down. Now I have to turn my hand in such a way that I can curl my fingers in the direction of the B field, which is out of the board. So I turn my hand around this way, point my fingers outward, and then my thumb points to the right, which means that the force on that charge will be to the right. All right, next example. Here we have a positive charge, so I use my right hand. I point my fingers in the direction of the velocity, which is upward. Now I have to turn my fingers in the direction of B field, which is downward. But now we realize that the B field is down, the velocity is up, the angle between them is 180 degrees. So we have an angle here that goes from there all the way to here, which is theta equals 180 degrees. And of course the sine of 180 degrees is 0, and therefore there is no force. So here we can say that force equals 0. No force on that one. All right, next charge. We have a negative charge, so I use my left hand. I point my fingers in the direction of the velocity, which is down. Now I curl my fingers in the direction of the B field, which is this way. Now even though it's not a 90-degree angle, it's not a 180-degree angle, so the sine of something between 90 and 180 is still a valid number, somewhere between 0 and 1, so I will have some sort of force, and my thumb is pointing outward, so I can say that the force on this charge will be outward, so force is out of the board. I indicate that with a dot. Sometimes we indicate it with a dot with a little circle around it, like the tip of an arrow. All right, now, next example. Positive charge, I use my right hand. I point my fingers in the direction of the velocity, and then I have to turn my hand this way so I can turn my fingers in the direction of the B field, which is out of the board, and the force in that case will be up. And finally, last example here, let me move over this way. We have a negative charge, so we use left hand. We point our fingers in the direction of the velocity of the negative charge. Now I have to turn my hand in such a way, I guess I'll have to come this way. Sometimes anatomically it's hard to do these things unless you stand correctly. So fingers in the direction of the velocity, then you point your fingers in the direction of B field, which is into the board, and it looks like my thumb is pointing this way, so this charge will feel a force in this direction. There. So hopefully that clears it up for you. Whenever you have a moving charge in a magnetic field, the charge will feel a force as long as the direction of the velocity is not parallel with the direction of the magnetic field. And to find the direction of the force on the charge, you either use your right hand or use your left hand. Right hand for positive charges, left hand for negative charges. Point your fingers in the direction of the velocity, then curl your fingers in the direction of the B field. Your thumb will point in the direction of the force. So that's called the left or right hand rule for finding the force on a charge, or the direction of a force on a moving charge in a magnetic field. All right, now we go on and actually start calculating some of the actual magnitude of these forces and direction of the forces in some examples coming up in the next video.